Welcome back to Very Ordinary Differential Equations. In this video, we learn about integrating factors. So suppose you have the differential equation, m of xy dx plus n of xy dy is 0. If the equation is exact, if dm dy equals dn dx, we know how to proceed. We covered that in the previous video. But what if the equation isn't exact? Well, an integrating factor is a function mu of the two variables x and y, so that if you multiply everything by mu, the result is now an exact differential equation that you can solve. So it's called an integrating factor because it's a factor. We're going to multiply everything by it. And it's an integrating factor because once you multiply through by mu, you should get something which is exact and you can then integrate. Now when mu is 0, you get a pretty uninteresting equation. You'll get 0 equals 0. So we do require that mu of xy is non-zero everywhere in our domain. Assuming that mu of xy is never 0 will actually guarantee that solutions to the original equation are the same as solutions to the new one. In other words, if I find an m and an n that solve this, it will also solve the one we began with up here, because you can divide both sides by mu of xy because mu of xy is never 0. So we do require that mu of xy never be 0, not just is sometimes non-zero. It must never be 0 in order for this following technique to work out. Well, how am I going to find that mu of xy? So let's suppose that we do actually end up with an exact equation after we multiply by mu. We haven't found it yet, but let's just suppose we did and it worked. Well then, if this is an exact equation, d by dy of mu times m must equal d by dx of mu times n. Applying the product rule to both gives me d by dy of mu times m plus mu times d by dy of m equals d by dx of mu times n plus mu times d by dx of n. You can rewrite this as mu times my minus nx equals mu sub xn minus mu sub y m. Now, given that m and n are known, okay, they were in the original problem and they're actually staring you in the face, okay, you're trying to find mu. What you have is a partial differential equation, a differential equation that involves derivatives that are partial derivatives, mu sub x and mu sub y. We're really not equipped to solve this in general. This is not a course on partial differential equations. It's a course on ordinary differential equations. So we want to find the solution to all of this, but we don't really want to get into the weeds of partial differential equations. So we can't approach it in general, but let's make some simplifying assumptions that will make it into a problem we can solve. Specifically, we're going to assume that mu of xy can be separated, specifically separated into a function of x times a function of y. So hopefully, whatever this integrating factor mu is, it can be written as function of x times function of y. So perhaps there is no such solution, but let's go ahead and presume that there is. We're trying to make assumptions to simplify our problems, so we're going to assume that mu can be written this way. Well then, mu sub x is just plain old x derivative of p times q of y, since q of y is presumed to be a constant for the x derivative, and mu sub y is just p of x times the derivative of q. So our problem is now to solve the following. We want m sub y minus n sub x to be, well, at the top, we have mu xn minus mu ym, but mu x is just this, and mu y is just this, which simplifies down to p prime over p times n minus q prime over q times m. Remember, you're also going to substitute this denominator of mu for p times q. So if we assume first, an integrating factor exists, and second, it can be separated as p of x times q of y, we've determined that what we have to solve is this right here. Now let's denote little p of x to be p prime over p for the capital P, and little q of y to be capital Q prime over capital Q. So now we have this expression right here, m sub y minus n sub x, which is something you can simply compute from your original problem, should be equal to little p of x times n minus little q of y times m. Observe that little p of x is p prime over p. That means it's the derivative of the log of p of x. So p of x is actually plus or minus e to the integral of little p of x. Okay, so whatever this little p is, it's capital P prime over capital P, and we were hoping to find our integrating factor. We were hoping to find capital P. But capital P of x must be plus or minus e to the antiderivative of little p. Similarly, capital Q of y will be plus or minus e to the integral of q of y dy. So, if we assume our original equation of m dx plus n dy equals 0, first of all, has an integrating factor. Second of all, the integrating factor can be separated into some capital P of x times capital Q of y. We've determined that m sub y minus n sub x must be little p of x times n minus little q of y times m, where capital P of x is plus or minus e to the integral of little p, and capital Q of y is plus or minus e to the integral of q of y. But all the work we've done is actually quite reversible. In other words, if we can write my minus nx is a function of x times n minus a function of y times m, then if I define capital P to be plus or minus e to the integral of this little p, and I define capital Q of y to be plus or minus e to the integral of this little q of y, then capital P of x times capital Q of y will be an integrating factor for our original differential equation. So in short, if this differential equation has an integrating factor, and that integrating factor can be written as capital P of x times capital Q of y, that will work out if and only if my minus nx is a function of x times n minus a function of y times m. And then I can compute capital P and capital Q through these exponentiated integrals. So from the original equation, what we now need to know is it actually possible to write my minus nx in the form that we need? So if we can write m sub y minus n sub x as a function of x times n minus a function of y times m, then we can find the integrating factor by going through a bunch of work. Solving for p and q can actually be quite difficult and really test your algebraic manipulation skills. Whatever my and nx are, okay, you just compute these partial derivatives and you hope that through sheer cleverness you can figure out a p of x and a factor of n, the original function n, minus q of y and the original factor m. But let's just suppose, again, simplifying assumptions, that my minus nx over n only depends on x. Okay, so if I take this expression here and I divide by n, and on this side I get my minus nx over n, and I assume that this only depends on x, well then q of y must have been 0, because on this side there's no more dependence on y. So we can set whatever this ratio is to be p of x and let q of y be 0. Similarly, if I were to divide out by m and get something that only depended on y, I could take that to be minus q of y and set p of x to be 0. If neither of these things works out, well then we're in for a challenge. Okay, but hopefully, if you compute my minus nx, divide out by n, and what remains only depends on x, set that to be p of x and let q of y be 0, and then proceed. Or take m sub y minus n sub x, divide out by m, and if what results depends only on y, set that to be negative q of y, let p of x be 0, and proceed. And you really hope that one of these two things happens. So overall, let's review the process. Begin with the differential equation m dx plus n dy equals 0, and suppose it isn't exact. An integrating factor would be a function mu, so that if you multiply through by mu, the result is exact. Finding such a mu, in general, is a partial differential equations problem and very hard. But if you can write m sub y minus n sub x is a function only of x times n minus a function only of y times m, then you can compute capital P, you can compute capital Q, and you can set mu to be their product. Then you'll have found an integrating factor. If you find an integrating factor, you can produce an exact differential equation which you can then solve. In order to find these P's and Q's, if my minus nx over n is a function only of x, just let that be P and let Q be 0. Conversely, if nx minus my over m depends only on y, use that for q and let p be 0. Notice compared to the previous slides, I multiplied this by -1 to change this order, and now that is just going to be q of y, not negative q of y. If neither of these things works out, you just kind of have to try and figure it out, and it might not even be possible. Once you find an integrating factor of capital P times capital Q, find solutions to that new exact equation, and solutions to the original will be exactly the same as solutions to your new exact equation. So even once you find your integrating factor, it's worth pointing out the problem isn't done. Finding the integrating factor just allows you to conclude that this expression here is exact, and then you can solve that. Okay, let's try some examples. Find solutions to x e to the y dx plus x squared e to the y dy is 0, and we're going to assume that x is positive. The equation isn't exact. If I take a y partial of that first term, I just get x e to the y, and if I take an x partial of the second, I get 2x e to the y, and those are not the same thing. So what we should check is m sub y minus n sub x over n a function only depending on x. Now we've already computed m sub y and n sub x e to the y, 2x e to the y. So this difference will be x e to the y. I divide this by n, which was x squared e to the y, and this simplifies down to just negative 1 over x. And hey, that does in fact depend only on x. So I set that to be p of x, and I let q of y be 0. Then I need to find capital P and capital Q. Well, capital P is plus or minus e to the integral of what I just chose little p to be. Okay. Integrating negative 1 over x gives negative log absolute value of x. We assumed that x was positive, okay, so this absolute value is going to be able to be dropped. Okay, similarly, q of y is plus or minus e to the integral of q of y, but that's just 0. Integrating 0 is just any constant, but we can go ahead and assume it's just 0, and we get plus or minus 1. And again, since we were given x is positive, the absolute value can be dropped. Okay, so we only need one integrating factor. So let's take p of x is 1 over x and q of x is 1. Take their product, so mu of xy is just 1 over x. So we found our integrating factor mu, 1 over x. Having found our integrating factor to be 1 over x, multiply the original differential equation by this. It cancels an x out of both terms, and you get e to the y dx plus x e to the y dy. This is now an exact differential equation. It's worth checking this to make sure we haven't made any mistakes along the way. So I take d by dy of that first term, and I get e to the y, and I take d by dx of the second, and since I'm doing d by dx of this term, e to the y is a constant, and the derivative of constant times x is whatever that constant is. So lo and behold, indeed, we now have an exact differential equation. Now that we have an exact differential equation, we solve it using the earlier techniques. We find an f of xy so that f sub x is m and f sub y is n, e to the y and x e to the y respectively. It doesn't take too long using those earlier techniques to find that capital F of xy is x e to the y. We're just kind of skipping all of the work because this is an earlier technique. So we found solutions to our new exact differential equation. And we know that solutions to our new exact differential equation are exactly the same as solutions to this one here. Okay? The only difference between these two equations is multiplying by x. And since x is positive, you can just divide an x out here to get this, and it's exactly the same equation. So solutions are given by x e to the y equals a constant. Another example, solve the following initial value problem. The sine of y times the cos of x dx plus the sine of x dy is 0, given y of pi over 2 is 3 pi over 2. Let's verify that we don't just have an exact differential equation. D by dy of the first term will be cos y cos x, and d by dy of the second term will just be 0 because it's just a sine x, and I'm taking d by dy. And indeed, cos y cos x and 0 are not in general the same thing. So let's check if m sub y minus n sub x over n can be written as a function only of x. Well, m sub y and n sub x are given by cos y cos x minus cos x. N was just sine x. This works out to be the cotangent of x times the cosine of y minus 1. which definitely still has some y's left over. It doesn't just depend on x, so this won't quite work. So we saw that m sub y minus n sub x over n doesn't only depend on x, it still had y's. So now we check if nx minus my over m depends only on y. Now in the previous slide, we already computed nx and my, and we just have them in the opposite order here. But now we're dividing by m, by sine y cos x, and actually this cosine x cancels out of everything, leaving behind cosecant of y minus cotangent of y, which only depends on y. This means I'm going to let little p be 0, and I'm going to let little q be this function right here. And I compute capital P and capital Q by taking e to the integral of those things. Now, e to the integral of 0 is just going to be e to the 0 is 1, so capital P of x is 1. Q of y, however, is going to be e to the antiderivative of cosecant y minus cotangent of y. This takes a little bit of work. We've let capital P be 1, but capital Q is this pretty nasty expression that we have to evaluate. So let's attack that integral up in the exponent. The first thing we do is multiply numerator and denominator by sine of y. So now I have 1 minus cos y over sine squared y times sine of y, and we're trying to integrate this. But that sine squared can be replaced with 1 minus cos squared. 1 minus cos squared is a difference of two squares. It factors as 1 minus cos times 1 plus cos. And now I can cancel the 1 minus cos in the numerator with the 1 minus cos in the denominator. So now we just need to integrate 1 over 1 plus cosine of y times the sine of y dy. If I do the substitution u equals cosine of y, this works out pretty directly to just be negative log of 1 plus cos y in absolute value. Now what's capital Q? Capital Q is plus or minus e to all of this. When I take e to all of this, I'm going to take this minus 1 and absorb it in here as a power. So then I'll have 1 over 1 plus cos y, and then e and the natural log will cancel out. So Q of y is plus or minus 1 over 1 plus cosine of y. And remember that capital P of x was 1. So our integrating factor is plus or minus 1 over 1 plus cos y. Our integrating factor can be either of the two things. Let's just take the positive one. So our integrating factor is 1 over 1 plus cos y. Multiply the original expression by this integrating factor. So here's our new differential equation where we've multiplied through by our integrating factor. This is now an exact differential equation, okay, which you should be able to check that the y partial of this equals the x partial of that. It will work out, this is exact, so what we need to do is find some capital F so that its x derivative is my first function and its y derivative is my second. We use the techniques from the previous section, what I termed as integrate, differentiate, integrate. And you'll find that capital F should be sine x sine y over 1 plus cos y. Okay, at this point, you can just double check that an x partial of this would be exactly that, and a y partial of this would be exactly that. Since we found an integrating factor, 1 over 1 plus cos y, we multiplied through and got this exact equation. We found that this function, sine x sine y over 1 plus cos y, has the desired partial derivatives, so solutions to this exact equation are given by setting that function to be a constant. And solutions to the exact equation are exactly the same as solutions to our original. So now we can use our initial values by setting x equals pi over 2 and y equals 3 pi over 2 and plugging them in here. Okay, the sine of pi over 2, that's just 1. The sine of 3 pi over 2 is negative 1, and the cosine of 3 pi over 2 is 0. So we quite directly get c is minus 1. So the problem is done. Solutions to this problem up here are given by sine x sine y over 1 plus cos y equals c, and I just replace c with minus 1. As a third example, let's find the general solution to x squared y dx plus xy cubed dy equals 0. Now, it's not an exact equation. If I take d by dy of that first expression, I get x squared. If I take d by dx of the second one, I get y cubed. X squared, y cubed, just different things. So let's check if my minus nx over n depends only on x. Well, m sub y minus n sub x over n is x squared minus y cubed over xy cubed, which still has a y in it, so no luck there. Let's check nx minus my over m to see if it only depends on y, but unfortunately, no luck there either. Okay, nx minus my is going to be y cubed minus x squared. Divide by x squared y, and there's definitely still x's left. So neither of our things that we've tried has worked. So my minus nx over n didn't only depend on x, and similarly, nx minus my over m did not only depend on y. What can we do at this point? Well, our only hope is to find some solution to my minus nx is some function of x times n minus some function of y times m. Now m sub y is x squared, n sub x is y cubed, n is xy cubed, and m is x squared y. So here's what we need to solve. P of x can't possibly cancel any of the y powers, okay? So P of x is a function that only depends on x, so this y cubed can't be simplified or reduced. Similarly, if Q of y only has y's in it, this x squared is going to stay there no matter what. So since P of x can't cancel a y cubed, the only hope is to make P of x times x equal to -1. Similarly, since Q of y can't cancel the x squared, can I make negative Q of y times y equal to 1? Now those, thankfully, are pretty simple, okay? We want x squared to be minus Q of y, x squared y. We want this term, since this can't cancel any of those x's, this should have x's left over, which means I want it to be x squared. Since P of x can't cancel any of the y's, this term here is going to have y's left over, which should match the only term that has y in it there. Well, we can actually do this pretty straightforward. Q of y is -1 over y, and P of x is -1 over x. So we were manually able to solve my minus nx is P of x n minus Q of y m by setting P of x to be -1 over x and Q of y to be -1 over y. And now we just solve for our capital P and capital Q like we did before. Capital P of x is plus or minus e to the integral of P of x. Okay. If P of x is -1 over x, its integral is just going to be negative log x. Call that log of 1 over x. E to the log of 1 over x is just 1 over x, and we still have this plus or minus. Similarly, Q of y is plus or minus 1 over y. We can take either choice we want because we only need an integrating factor. We don't need somehow all of them. Okay, so we only need one solution, so let's just take 1 over xy. So here's our integrating factor, 1 over xy, multiply through. To get x dx plus y squared dy is 0, and this is now exact. It's easy to check. D by dy of x is just 0. D by dx of y squared is also 0, so it is exact. Now we need to find some capital F so that its x derivative is just x and its y derivative is just y squared. It's not very hard. You'll get x squared over 2 plus y cubed over 3. You can see directly now that its x derivative is just x and its y derivative is just y squared. So solutions to our new exact differential equation are exactly given by x squared over 2 plus y cubed over 3 equals constant, but those are exactly the solutions to our original differential equation. So there we have it. X squared over 2 plus y cubed over 3 is a constant is the general solution to our starting differential equation, even though that equation we started with isn't exact, and the two things we checked to make our lives easier, neither of them worked, okay? Mx minus ny over either m or n was not a one variable function. So we were a little out of luck for our easy technique, but thankfully the hard way, we were able to do it in this problem. In summary, what have we covered? If you have a differential equation, m dx plus n dy equals 0, and it's not exact, an integrating factor is some function mu, so that if you multiply through by mu, you do get an exact differential equation. We require mu to be non-zero on the entire domain. That will guarantee that solutions to the exact equation are the same as solutions to the original equation. If you can show that m sub y minus n sub x over n depends only on x, you're going to set p of x to be whatever that was and set q of y to be 0. If, however, nx minus my over m depends only on y, set that to be q of y and let p of x be 0. Otherwise, just hope you can solve my minus nx equals p of xn minus q of ym. One of these three things, either you've set p of x to be this function and q of y to be 0, or this to be q of y and p of x to be 0, or you just managed to solve this, you've got a choice for p of x and you've got a choice for q of y. Compute capital P and capital Q to be plus or minus e to the integrals of those things. Then make either choice for capital P and either choice for capital Q. You've got an integrating factor now of capital P of x times capital Q of y. Multiply through by that, get an exact equation, solve the exact equation, and you have solved your original.